I'd like to talk to you now a little bit about complex problem solving in organic chemistry and beyond, because it's really important not just for success in this course, but for lifelong learning success. You need to be able to solve complex problems effectively and at least generate reasonable solutions to complex problems in order to be successful in today's world. And so, believe it or not, organic chemistry might be one of the first courses, and certainly one of the first physical science courses, where you encounter really deep heuristic problem solving. And heuristic problem solving is different from the kinds of problem solving you've done already, and I hope to prove that to you in this video. So think back to the general chemistry course that you took maybe 1 or 2 or more semesters ago. In general chemistry, your instructor probably explained to you in qualitative terms concepts like concentration and chemical kinetics, maybe the ideal gas law. You were explained all these concepts qualitatively, meaning the theory behind them was explained to you. But then there's a good chance that when you got into the exam room and sat down to take the exam, or you did homework, or you attacked any other sorts of problems in your Gen Chem course, you understood that there was information given to you in the problems, and there was a process that you could execute, or an algorithm, more specifically, that you could execute to get from the information that the problem gave you to a correct solution. This is algorithmic problem solving. It's algorithmic because there is a process whose steps are rationally determined and logical and set for every type of problem in that class. And so a computer or a machine could execute algorithmic problem solving, right? Pulling out the relevant information from the problem statement, going through the steps, and arriving at the solution. And perhaps more importantly, when a mistake is made, imagine a machine doing an algorithmic problem. When a mistake is made, that indicates a bug in the computer code, right? A problem with a particular step of the process. When there's a problem with, let's say, step number 2 in some algorithmic process, the person who wrote the computer code is going to go back to step number 2, re-examine it, and fix the bug. The same mental process happens to students in general chemistry who are having issues solving problems. They think back to each step of the algorithms they use to solve problems that they're having trouble with and ask, am I doing something wrong in this particular step? If so, I need to practice it again until my algebra works, right? This kind of algorithmic problem solving is not very applicable to organic chemistry, and in fact, we will offload almost all of the algorithmic kinds of problems that we encounter in organic chemistry to machines. The situation in organic chemistry is very different. In organic chemistry and beyond, for complex fields like medicine and dentistry, pharmacy, the problems are more often what we call heuristic in nature. What is meant by this term heuristic? Well, a heuristic is just a general rule that maps a certain set of information onto an idea or a theory. That then suggests a solution. And heuristics are hazy. They may apply, they may not apply. And moreover, a variety of heuristics often apply to a given set of information, some of which may contradict others. And so heuristic problem solving is a matter of applying general rules to information that you're given in problems and arriving at a solution that may not be the only solution, right? In this sort of hypothetical example, I've generated 2 solutions that are independent of one another, but based on what we know already, based on the foundational theory that we have, one of our solutions we have to judge is the best. And so this is heuristic problem solving in a nutshell. What it really looks like in practice is something like this. You begin with a very complicated problem with a lot of information embedded within it. There might be a variety of ways that you get off to a start with these sorts of problems. You can use intuition, for example, the visual relation between an example you're working on now to things that you've seen in the past. You might use an analogy, which relates information in the problem to information that you've seen in other kinds of problems. You might dive into a detailed analysis where you use foundational ideas to begin really picking apart the different pieces of information in the problem. And each of these methods could lead to a unique solution. You'll have to choose one of these options as the ideal before you can move on. And making this choice involves a fair bit of risk. But it's a risk that you're going to have to take. As a doctor, diagnosis is inevitable and mandatory, right? You'll have to choose one of the options. You choose an option, you execute it. You execute what it's telling you to do. There might be an algorithm involved at this stage, but note that the choice you made concerning what to do was more of a heuristic choice based on what you had seen already in the general rules that were in your mind. And then you arrive at a solution, your final solution, and then you evaluate that. And if you encounter uncertainty, it might be time to execute again. On the other hand, if you understand that your solution is incorrect, you may need to go all the way back to those original rules that you used to generate the possible solutions in the first place. And so you can see that this is a much more rich and involved process of heuristic problem solving than the algorithmic situation where the process is well defined. Now, our task as organic chemists and as complex problem solvers is to understand the examples that have been executed already, how we can use strategies like analogy, intuition, and detailed analysis to arrive at possible solutions, and then really to take this step of choice and understand how to evaluate the different methods against one another. Myself, I'm very partial to being systematic. I like beginning with detailed analyses of a few examples and then using analogies to extend those to a wide variety. My hope is that in the first week of Chem 332, you will come to see that the massive variety of possible examples of molecules and reactions that we see in organic chemistry can really be explained by a fairly small number of seed examples, which we'll deal with in this category of detailed analysis. Of course, moving beyond that first week, we'll begin to make analogies, and in particular, the entire second half of the semester will make analogies between different types of structures that are found in bioorganic contexts. So we'll make analogies between the nucleic acids and the carbohydrates, between the carbohydrates and the amino acids, etc.